So, let the other students be joining. We'll start the session for today. So, uh, a very good afternoon to all the students. And this is the second week for the live interactive session on chemical engineering thermodynamics. So today what we'll be doing is that we'll be going to the week 2 content. Already week 2 assignments has already been solutions is uploaded. So what we'll do is that we'll go through some of the week 2 contents, the lecture notes, the content or the topics that has been covered during the week 2, and some of the assignment problems and some of the tutorials related to that topics. Okay, so in the previous week, like what we discussed is that what is chemical engineering thermodynamics, why thermodynamics has been studied in chemical engineering, and what engineering students can get benefited from this course. So it's one of the basic fundamental core course which chemical engineers has to take during the undergraduate studies. Apart from this, there are also different courses related to the same thing, that is advanced chemical engineering thermodynamics also, which will come if you want anyone wants to go for the, you can say, post graduation studies or higher studies. So but this course is like a core course for the chemical engineering undergraduates all over India as well as from all over the world. So we discussed in the last live interactive session, that was the first interactive session for all of us, that what is thermodynamics, laws of thermodynamics, which includes zeroth law of thermodynamics, first law, second law, and third law, various terms which will come up on during the numericals, and various concepts in thermodynamics which are much common terms, and some of the concepts related to the week 1 content. So in this week what we'll do is that we'll go through some of the content and the lecture notes that has been covered during the week 2. We will solve some of the numerical problems associated to that, and then we'll try to wind it up as soon as possible for the week 2. In the meanwhile, in between, if you have any of the questions related to any of the thing, suppose if you face any issues related to solving some of the assignment problems related to week 1 and week 2, I'm really happy to help you out. But the thing is, make sure that the assignment due date has been over. So what we'll do, we'll start with the week 2 content as of now. So I welcome you all on the NPTEL online live interactive session on the course on chemical engineering thermodynamics. So just a quick overview. So this course has been offered by Professor Gargi Das, who is she's a professor in the Department of Chemical Engineering at IIT Kharagpur. And a little bit about myself, I'm your teaching assistant for the entire course duration from Jan to April. So I'm Rakshit Shivam Kumar, and I'm a PMR scholar in the Department of Chemical Engineering at IIT of Madras. So like I said, like I introduced in the last live interactive session, is that I'll be the TA for the live interactive sessions. So we'll be having these live interactive sessions every weekend on Saturday, that is from 3 to 5. So we'll be solving some of the numerical problems, assignment problems, tutorials, and some of the concepts related to that big content. Okay, so we'll start from the week 2. So the week 2 content that has been uploaded in the Thermodynamics portal is as follows. So it talks about the entropy change during a spontaneous process. So we'll see what is entropy, and what happens during the spontaneous process in the change in the entropy. So this has been covered during the week 2 content. According to that, there is another term which is called as spontaneity. So the criteria for spontaneity processes in chemical engineering thermodynamics has been discussed during the week 2 content on NPTEL SWAYAM portal. And there is another term called the thermodynamic network. So there will be a different network of different terms like enthalpy, entropy, internal agent energy, Gibbs free Helmholtz energy, Helmholtz free energy. So how these things are interconnected, that is called as a thermodynamic network. So you'll see that I will show you some a simple way to represent the thermodynamic network, so that it will be better for you to like you don't need to mug up anything, just need to relate some of the terms with to each other, and that is called a network of like the properties of the thermodynamic network. Okay, and then we'll solve some of the practice problems related to the assignments of the week 2 and some of the tutorials that have been taken from different reference books. Okay. So the first thing, that is a criteria for the equilibrium. So the first thing that you know, after determining the laws of thermodynamics, various terms and concepts, and the process is like reversible, irreversible, what is equilibrium and what is the criteria for equilibrium. So there are 3 different types of equilibrium like I have mentioned up here. The first is mechanical, second is thermal, and third is chemical. So the mechanical equilibrium corresponds to the equability of the pressure. So sorry, so this is typo mistake. So if there is an equilibrium in terms of mechanical, we'll say the system is in mechanical equilibrium if the pressure are equal. Suppose if P1 and P2 are same, you can say the system is in mechanical equilibrium. Suppose if I say the system is in thermal equilibrium, thermal means heat. So you can say that the H1 equal to H2 or T1 equal to T2. In simple terms, thermal means heat. That means the temperature of the system 1 and system 2 must be same. So the temperature is one of the driving force in terms of thermal equilibrium. So we can say that the temperature is the driving force. The third one corresponds to the chemical equilibrium. So when terms arrive, what is chemical equilibrium is that there is a term called potential. So the chemical potential is defined as a driving force. So in all these cases, you mention or should consider one of the things which are the driving forces for the equilibrium. For mechanical equilibrium, the driving force is pressure. Okay. For thermal equilibrium, the driving force is temperature, and for chemical equilibrium, the driving force is chemical potential. So these are some of the terms that can be asked directly into the final examinations in the form of MCQ, or they can be given in the form of numerical questions. Like suppose the system has a chemical potential, or system is in thermal equilibrium or mechanical equilibrium. Then you know if the T1 and T1 is given, then T2 will also be the same because the system is in mechanical equilibrium. Similarly, vice versa, if you say the system is in thermal equilibrium. So the question arises, the system has a thermal equilibrium temperature T1 equal to this, and the system T2 is this. It's not given, so you should consider T2 equal to T1 because the system is in thermal equilibrium. Okay, so this is one of the basic point to remember as of now. Now, so what is shown is here how to determine the I shown in terms of like just the notes, like what is the driving force. For mechanical equilibrium is the pressure, for thermal equilibrium is the temperature, and for chemical equilibrium is the chemical potential. But if I take in the simple terms, if I need to show the help of some of the schematic diagrams, so I can show you here. So this is first we'll call the mechanical directionality, and second is thermal, and the third is chemical directionality. So this thing I have taken from one of the reference books that I was studying during my post-graduation studies, that is from Kodesky. I have given up the references up here. If you guys want to have a look out to this, please have a go look out. It's easily available, downloadable online. And please don't just directly mug up all the things. It's better. What I'm saying is that just go through the concepts. It's much way easier to go through the concepts than go mugging up the things. Okay, so like I said, mechanical equilibrium corresponds to the driving force as a pressure. So if I take one cylinder and the system the system is at a high pressure gas, which is in the cylinder shown up here. Okay, what I will do, if I open up this wall, what will happen, the pressure and the temperature inside will vary because the pressurized gas inside will find a space as soon as I open the valve to move out. So what will happen, the pressure outside is P atmosphere, okay, and the pressure inside is P1 suppose. So the pressure inside will equilibrate until it comes out to be pressure at outside. So this is called the mechanical directionality, and then the pressure inside and outside will be the same. So it's the driving force is the pressure. Similarly, if I take thermal equilibrium, if you take a brick which is at a high temperature shown up here, and if you give it to suppose another body, or keep it outside of some atmosphere which is at a temperature T atmosphere and P atmosphere, and suppose the temperature is T1 at highest temperature. So if the thermal equilibrium is there, what will happen? It will try to equilibrate and forms to T atmosphere. So T atmosphere is atmosphere as the surrounding atmosphere. So it will try to dissipate the heat towards the surrounding, and it will continue to dissipate until the equilibrium is reached. That is T equal to T atmosphere. Similarly, the chemical directionality, that is the what I can say is the chemical equilibrium. That is the driving force is termed as the chemical potential. So if you take two different gases, gas A and gas B, which in a cylinder, and I have a membrane separating between these two. Okay. So what will happen if I want to try to remove this membrane? So until in the system 1, you can see that the gas A and gas B are separated through a membrane. If I remove this membrane, what will happen is that the gas molecules of gas A and B will try to mix up with each other. In simple terms, what will happen is that they will try to equilibrate into each other, and they will mix up and they form a system called homogeneous system. And that after some point of time, there will be homogeneity gas mixture. So this is called the chemical directionality. That is called the chemical potential is terms of the driving force. Okay. So please remember all these things, all the three equilibrium concepts, and how this happen actually. So this is the simple schematic representation of the equilibrium, that is chemical, mechanical, and thermal equilibrium. Okay. Now So this is what we call as the thermodynamic uh, relationship. So all the things what have been shown up here is taken from the reference book which I have done during my post-graduation studies. But you can, because this kind of relationships are available in, and which is the basic thing that is available in all the reference books. It's not just like it is available here, but it's available in all the reference books. It's just I am shown here because it's coupled in one short quick view that you can able to identify. So what I've shown up here is the different thermodynamic relationships or thermodynamic network. So this is called thermodynamic. So what I've shown up here is the thermodynamic network. So these are the different things that you might be knowing in the lecture notes that are already discussed. Or as a just quick to show you guys what is the thermodynamic actually means is that, so if you see here there are three different relationships. There is the pressure, temperature, and the volume. So the first one relates the temperature, the second is pressure, and the third is volume. And I have given two different like sign configurations for that thing. So if you see here, if this is the, like what you can see up here is a cyclic relationship, and if this is called a Maxwell relationship. Okay, so whatever the arrows that is on the opposite sides, this corresponds to the Maxwell relationship. Okay, and this is called the cyclic relationship, what is mentioned up here in the cyclic type. So this diagram includes all the thermodynamic terms, that is enthalpy, entropy, pressure, temperature, volume, and various other terms, and how they are related to the relation without temperature, relation with temperature, pressure, and volume, and entropy. So this is what we call as a thermodynamic network. I don't want to go too deep into this because this has been derived from basically from the basic equations that like we have solved in the week 1 5 interactive sessions. Suppose h equal to u plus pv. From there you can partial differentiate and just derive the terms. You can arrive at this all the same points. So just you need to remember what is enthalpy, what is entropy, what is Gibbs free energy, Helmholtz Gibbs free energy. If you know all the basic equations of that, the definitions itself will define the equations, and from that equation you have to do the partial differentiation and you can arrive at different points. So from all those basic equations only we will arrive to able have this thermodynamic network. So I'm not able to derive right now here, but I've shown how this thermodynamic network looks like. So in the examinations, in some numericals comes up like you have to relate two of these things. Suppose you have been given this thing, del P by del T at constant entropy, you can directly relate with this thing. So what will happen is that you can, if the entropy is given to you, you can partially define entropy with respect to the constant pressure. So this is called the Maxwell relationships, and the cycle relationships also happens with that thing. So just remember the basic equations like the enthalpy, Gibbs free energy, Helmholtz free energy, and internal energy, and entropy. So these five are the basic equations. All these equations, do the partial differentiation, you will arrive at this point. Okay, so these are some of the thermodynamic networks that has been discussed during the week 2 content. Now what I'll do is that we will solve some of the numericals of the tutorial and some problems that has been discussed during the week 2. So the first we'll start from basics as of now. I don't want to just directly quick jump on some of the hardest numericals from the week 2 itself. So try to increase the pace as soon as the course content proceeds. Okay, so as like I said, from the week 1 and the week 2, it covers like the basics of thermodynamics, starting from the laws of thermodynamics, different processes, different terms, and in week 2 it covers the like the thermodynamic networks, chemical potential, and internship related to all these properties. So, we'll solve some of the numericals. So this is just like quick short points, but you have to remember this all these quick short points because in the final examination, it's not like just like the numericals, like the 5 marks numericals or the 10 marks numericals will come up suddenly. If you miss out this one or quick shorts, like MCQs, it's very hard to score big marks in the final. So please do remember all the concepts. That's the basic points in thermodynamics. So it will be helpful for you to arrive at a final point of the marks. So like last week I discussed types of a system, surroundings, and a boundary. So this is one sort of an example, like the quickest, simplest form of point of, because I want to brush up from the week 1 also, because from week 1, week 2, we're going to proceed up to like week 12. So I don't want to get like, if you when you go to week 12, you might have forgetting almost like past 10 to 11 weeks. I don't want to go to that. So that what we'll be doing is that we'll cover some of the numericals so that you will try to brush up. Okay, we have done some of the things in the previous week also. Okay, so this is the first question. So it defines hot water inside a closed thermoflask is an example of. So if I take a system which is closed, and if I say there is no heat and mass flow, so if I take this as system, I can say there will be no heat and mass flow because the system is isolated. Okay, so what will happen? There is no heat and mass flow into the system. So because it's a thermoflask, so thermoflask is insulated, and there will be no heat flowing into and out of the system. Apart from that, there will be no mass flow in and out of the system. So it's a typical example of what we call as an isolated system. And this is an example because many of us have been using thermoflasks during the winters while traveling in so many places, and now we'll be using water bottles that have comes under thermos. So the thermos is basically to keep this heat and energy in terms of energy and mass do not allow to flow from outside or inside to outside. It is from the external interaction between the system and the boundary, or the system and the surroundings. Okay, so that is called as an isolated system. So this is what I have shown an explanation here. That is the correct answer is C, because hot water inside a closed thermoflask cannot change mass and energy in the form of work or heat with the surroundings. So it is an example of an isolated system. Just the simplest question, but it might be someone might make a mistake because if they don't know what is open, closed, and isolated system. And because the fourth one is also the trickiest one. It's like depends on a content of the flask. If you don't know what is the content of the flask, if it's thermos or not, you can say okay, D is the correct answer. I don't know the correct answer. So that's not actually make a point. Don't make any assumptions if you don't know. It's better to go through the concepts if you have already known the concepts. Thermodynamics. Okay. Just 1 minute, is my system is hanging. Okay. Yeah. So which among the following is not an extensive property? So like last week I discussed, there are two different types of properties. One is intensive property and the extensive property. Other is extensive. So what is intensive property? So the intensive property is a property which depends upon the mass or the volume of the system, whereas the extensive property is independent of the mass or the volume. So if I give, suppose in the examination they give like 4 different MCQs to you. So like I said, what is Gibbs free energy, enthalpy, Helmholtz free energy, and chemical potential. So they have like different symbols like enthalpy, H, Helmholtz free energy, A, and chemical potential alpha, whatever you can define. So now out of all this we can say which is not an extensive property, because the chemical potential is one of the things. So if you see, if all the equation G is equal to H minus Ts, A equal to H equal to U plus PV, so all that depends upon the internal mass of the volume of the system. Apart from all those 4 options, on the chemical potential is the thing which is not an extensive property because it's depends upon the volume. So what will happen is that, yeah, so the correct answer is D. And the reason for that is the chemical position is intensive property and is an independent of an extent of the system. Apart from this, another term that can be used, independent of the extent of the system, is independent of the mass. So please remember these 2 points, intensive as well as extensive, that is basically related to the mass and the volume of the system. Okay. So this is the simplest one. Another again, what is an adiabatic? First of all, instead of going to read the entire question, make sure you have written this term. What is adiabatic? Adiabatic means there is no heat flow in and out of the system. So the Q equal to 0 for an adiabatic process. Okay. Now the reversible process. So if I take state 1 and I have to go from state 1 to state 2, I go through this path, and by coming back from state 2 to state 1, I follow the same path. If it is called a reversible process. Okay, so it follows the same path from state 1 to state 2, state 2 to state 1. So the process is called a reversible process. But here now the thing is, it's mentioned reversible adiabatic. So if I take see the options, you try to relate with some of the concept that has been already discussed. So entropy, like S equal to Q by T. Okay, and if I partially differentiate. Okay, now we have gained an adiabatic process, so this terms has to be 0. Therefore entropy of the universe continuously goes on increasing. That is one important point that has been discovered in the week 1 content. Now it is a reversible process. So what will happen is that a reversible adiabatic process is an predominantly an isentropic process. You can see if you know the concepts, it's just because if you click in your mind, okay, that is an adiabatic process, that is Q equal to 0. And if you look at the option that is mentioned up here, you can relate Q with some of the options, because entropy is related by ds equal to dq by t. So entropy is 0, ds is greater than equal to 0. That is the entropy of universe continuously goes on increasing. So what will happen is that ds should be greater than equal to 0. So the process is termed as isentropic process. So it's just like basically what I've given up. So dq equal to 0 for adiabatic. The entropy of universe goes on increasing because ds equal to dq by t equal to 0. Hence a reversible analytic process can also be called as a constant entropy process or an isentropic. So because these terms, what I've been mentioning up here is because we have already discussed in the week 1 lecture content. I've also shown you what is isobaric. This is the constant pressure. Isentropic is constant entropy. Isothermal is constant temperature, and isochoric is constant volume. Okay, so these terms you have to remember because it will directly come in the final examinations directly like these terms. It will not come like adiabatic process. There is a constant temperature, there is constant pressure, constant volume, or constant entropy. It will come like this terms. So if you don't know what is this terms and how what they resembles about, it will be difficult for you to arrive at a final answer. Okay, yeah. So this is also related to some of the week 1 content. So so the degree of freedom, yeah. So it's like I already discussed what is degree of freedom. It's better to go directly solve these questions. Okay, so the degree of freedom is given by f equal to c minus p plus 2, where c is the number of components, p is the number of phases, and f is the number of actual variants required to solve the question. Now if you see at question 1, what is the degree of freedom of a system comprising of a closed container half filled with boiling water and water vapor at the top? So if you see the number of components is water. Okay, so see component is 1. Number of phases, that is water and water vapor. Boiling water and water vapor are 2 components. And we are given by 2, that is these points correspond to pressure and temperature. If I equal to 1 minus 2 plus 2, therefore degree of freedom equal to 1. And take the second question, estimate the degree of freedom in the water in the container is replaced by a salt solution. So if I take a salt solution, suppose NaCl, so sodium chloride in water, because it's a solution actually, so there will be no salt alone, it will be water. So the number of components is now 2, phases, number of components, oh sorry, plus 2. So estimate the degree of freedom, the water in the container is replaced by salt solution. Yeah, so here there is somewhat, I just got tricked because it's a salt solution. But please remember, if a solution is given, there will be 2 different things. Just take as NaCl or KCl plus H2. So the components are 2 components, NaCl and water. So number of components is 1, number of phases is 1. So what will happen is that So we'll just see this thing. Yeah. So what I will mention up here is that the first one that I already discussed. So number of components is water and salt, and P is the number of phases. Okay. So what I did is that I'll not mention specifically. That's what I've been mentioning here about is that. So it's the same question related to the one, but only thing is that the water solution is being replaced by the salt solution. So the number of phases will be 2 itself. So what will happen? The number of components is 2, number of phases. So this turns out to be, that's what I mean. It's like mismatching here. What something is missing in the question. So it's directly related to the question one. The only thing is water is related to the water solution or salt solution. So if I take NaCl or KCl plus water, the number of components will be 2. Earlier it was only water. So now here is salt solution turns out to be NaCl plus water is 2 number of components. Number of phases is like boiling water and water vapor and plus 2. So the degree freedom turns out to be 2. So this is what I mentioned up here also. Okay. Number of components 2, water plus salt. Number of phases is liquid, salt solution and water vapor. And similarly the first one also we have mentioned up here. Okay, so these are some of the like just like quick shots, like 1 or 2 marks you can get easily in the examinations. Okay. Okay, another one. So just quickly go through the question what has been asked. It's related to the processes, the equations that has been covered during the week content. So there is one equation that has been given to us, that is PV raised to 1 by n equal to constant. Okay, so now these terms will arrive till the end of this course, like I've been saying. Please remember what is the specific things about. So first is called as isochoric. So isochoric means volume is constant. Now if you take the equation P raised to 1 by n equal to constant, volume is, so for isochoric problem volume is constant. So what we'll do is that 1 by n equal to infinite. So n equal to 0. So this is the first answer because the volume is constant, right? For isochoric process, if you take volume is 1 by n equal to constant, what will happen is that 1 by n is equal to infinite and n will be 0. So the first answer is C. Now if you take the second one, isobaric, pressure is constant, okay, for isobaric process. Therefore, PV raised to 1 by n equal to constant. Therefore, what will happen is that 1 by n will be 0 and n will be infinite. Pressure is constant. Similarly, in other terms, you can derive like for adiabatic, what will happen is that I'll just write up here for adiabatic Q equal to 0. Okay, so PV raised to 1 by n equal to constant. Therefore, in place of n, I can replace directly with the gamma. So 1 by n to gamma, therefore n equal to 1 by gamma. And isothermal, temperature is constant. So Pv equal to 1. Because the temperature is constant, you can directly lead with this equation. So these are some of the simplest terms you need to know, this directly matching with it. And this question has been run many times in the GATE examinations as well as in some of the aptitudes, not the aptitudes but in the various entrance examinations all over India. So just quickly remember, so there are different values coming in the numerator of this volume is to 1 minus gamma by gamma, 1 minus n by n, and 1 minus 1 by gamma. You have to just relate what are different processes and just relate what these things to the right of final answer. So this is what just I've given an explanation of that. Okay, so the correct answer is this one here. This K and D, like I've solved in the previous one. Okay. So the reason why I'm showing up this thing is that just only it might be looks easiest to you, but when it comes to the final examinations or some of the entrance examinations, many students makes mistakes in just quick questions. So it's better just to go from the concepts. Don't mug up. Just go through the concepts. Remember some of the specific terms in chemical engineering, thermodynamics. That will be used in thermodynamics only. That can be used anywhere else. But if you don't know the terms, if you're like, okay, I will do this during prior 1 hour, 2 hour before the examination, it will be helpful for me. No, that's not going to work out. So just go through the concepts each and every day. I'm saying not saying if you need each and every day, but if a week content is over in the NPTEL swim model, just go through the week lecture content prior one day arriving to the live interactive session, because when I was solving it today, you just get clicked in your mind, okay, this is the concept that has been discovered and I know these concepts. Okay. Yeah. So now we'll solve some of the numericals related to the week one and week two content. Sorry. Till now we have been solving the MCQs, but now I will try to solve some of the numericals. So what has been given up here is that the molar volume of an organic liquid at 300 Kelvin and 1 bar is 0.1 meter cube per kilomole, and beta, that is volume expansivity beta. So there are two different terms, beta and gamma, right? You might have gone to the lecture notes, you have seen beta and gamma. So beta is volume expansivity beta and isothermal compressibility K, or kappa, you can say. Some will represent with the kappa or K or gamma, right? So please remember these two terms. Calculate a change in the entropy in joule per kilomole Kelvin. The pressure is increased at 220 bar. So P1 is given 1 bar, P2 is given 20 bar at constant temperature of 300 Kelvin. So the temperature is constant and is given as 300 Kelvin. Assume del V by del T at P is constant in the pressure range of 1 to 20 bar. Okay. So now we have to determine the molar what do you do? Assume constant. Change in the entropy. We have to determine the change in the entropy. So what we'll do is that we'll solve the question. So molar volume is given as 0.1 meter cube per kilomole. Okay. Now I told you there are two different terms like volume expansivity beta and isothermal compressibility kappa. So coefficient of volumetric expansion that is given by beta equal to 1 by v del u by del t is equal to given to us as 1.25 10 is to minus 3 per Kelvin. Okay. So this is what we call as the volume expansivity beta, or coefficient of volumetric expansion. Now what we'll do is that since we have del u by del t p equal to 1.25 10 is to minus 3 to v. So the molar volume given us, so this is molar volume and we have molar volume in this term. So we multiply it with this, it comes out to 0.1. So this is 1.25 into 10 is to minus 4 meter cube per kilomole into Kelvin. Now we need to determine the change in the entropy. Okay, so from the now I've shown you the thermodynamic network. So what we'll do is that from Maxwell equations or the Maxwell relationships, from the Maxwell equation we have like volume expansion del U by del T at P equal to minus related to the entropy. Okay, so this is from the Maxwell relationship what I mentioned up here. Okay, and I've shown this thing thermodynamic network because I know the value of del U by del T at P from the volumetric expansion, and I can relate directly with the change in the entropy del S. Okay, so what I will do is that minus del S by del P at T equal to minus that will be positive. So this is minus, I will take 1.25 into 10 raised to minus 4 meter cube per kilomole Kelvin. Now I am to determine the change in entropy. So dS equal to minus 1.25 10 is to minus 4, and the change in the pressure is given to us as, so P1 is 1 bar, P2 is 20 bar. Okay, so change in the pressure is P2 minus P1, so 20 minus 1 bar, and this is 1 bar is going to 10 is to 5 Pascal, so convert into 10 is to 5. Therefore ds comes out to be, if you calculate this, it comes out to be minus 237.5 joule per mole Kelvin. So we have converted into Pascal and we have taken the unit of joule. So what have been asked is calculate a change in the entropy in joule per mole Kelvin. Okay, so we have calculated that entropy, change entropy. So this question relates how we can determine using the Maxwell relationships and two different terms, that is the volume expansivity beta and isothermal compressibility K. I can also show you where I have mentioned that isothermal compressibility and volume expansivity in the thermodynamic network. Okay, so if you see this thing, yeah, you are seeing this equation, right? So this is what we are using right now, volume explicit equation of state. So volume explicit beta is equal to 1 up beta equal to minus 1 upon v del by del t at constant pressure. Okay, similarly there are different terms like isothermal compressibility kappa. So if you know the thermodynamic relationships or thermodynamic network, it's very easy to solve this type of equations. Okay, so now we'll solve another one. Now this question asks related to the somewhat equation of state. So I not discuss equation of states, but like I've discussed like an equation of state for ideal gas equation of state, that is given by P equal to nRT. So this is the first general equation of state, that is the ideal gas equation of state we have discussed during the Levi-Cohen content. Okay, so now what I'm going to show up here is that how you can use different equation of states. There will be coming different equation of states in the later content lecture, which are like uh, Maxwell, not Maxwell. There's Redlich-Kwong, Sawyer-Redlich-Kwong, Pang-Robinson, and one more equation of state will be coming up. So there are like 4 different equation of states apart from the ideality, because that is this, because in real world the systems will deviate from ideality. None of the systems will be ideal. So this is just what an ideal equation of state corresponds to, the ideal gas law, that is PV equal to nRT. But all the systems are not aware the ideal system, right? In real world it will be non-ideal. So for the non-ideal systems we have different equation of state, that is called the Redlich-Kwong, Sawyer-Redlich-Kwong, Penn-Robinson equation of states, and they have their own derivations and all the things to solve the numericals. But the simplest term we are solving it right now is using the idealist equation of state only. So the question says for gas obeying the equation of state P minus P equal to RT. This one is much more related to the van der Waals equation of state. So that is the first one in terms of non-ideal system. Calculate the enthalpy change, enthalpy change and entropy change when the gas is taken from the state 1, which has a mention of pressure and temperature, to the state 2. Assume the specific heat at constant pressure is given to us as 40 kilojoule per kilomole Kelvin, or the temperature and the pressure range, and these. So this A and B in Van der Waals, so this equation is somewhat related to the Van der Waals equation of state, and A and B are Van der Waals constants. Okay, so we'll try to solve it out. First, we write what has been given to us. Okay, so what I will doing is that every time when we try to solve some of the questions, first of all, what we do is that we will just write up, because this question contains too many data points that has already been mentioned in the question. So if you don't mention what is given in the question in the form of like quick short points, it is difficult for you to arrive at a final answer, because it's better to write down what is given in the question first in terms of the points directly. So what I will do is that we'll write out. So we have been given equation as P equal to V minus P equal to RT, B equal to 0.2 meter per kilomole. Specific heat at constant pressure as 40 kilojoule per pressure P1 as bar, pressure P2 as 20 bar, temperature T1 as 300 Kelvin and temperature T2 as 400 Kelvin. Now, what you have to determine is a change in the enthalpy. So, enthalpy change given by TH CPT. Now you might be wondering where this equation comes from because I'm not aware of this equation as of now, but it has already been discussed in the week lecture notes. Not in the week lecture notes, but it will come up. So what I'll do is that we'll solve some of the concepts related to the non-analytic equation of states also. But just for like a quick overview how this apart from the ideal gas equation of states, there are many different equation of states also. So this question is much related to the non-ideality, and which has been equation that is given to us is the Van der Waals equation of state. Enthalpy change can be written as, so if you try to simplify this equation, what we'll do is that, so we'll try to simplify. Okay, I can write this as RT by P plus, I will take this on the base side, P minus RT by P. Okay, so what I've done, I will replace the using this equation of state, I have partially differentiated and I've simplified this equation. So now what I'm having is that dH equal to Cp dt. Now how this came is that these two terms will cancel out, the Cp dt and V into dP. So this is what I have written up here. So change in enthalpy, Cp is going to us as 40 kilojoule. So I will convert into joule, that is 10⁻³ into Tt. Temperature is given to us as T1 is 300, T2 is 400. So what I'll do is that, okay, I will let be in, I'll not convert. What I'll do is that 40, what is T2? 400 minus 300. dt is T2 minus T1. V has been given to us as 0.2. And pressure is given to us as 20 and 10. So 20 minus 10 is 10. And that is in bar, so we'll convert into Pascal. Okay, and this 0.2 is in meter cube per kilomole. Okay, so that's divided by 1000. So it will be, so in order to make all the things in one specific units, so if you try to solve it out, it will come out to be directly, you can directly use the scientific calculators that isn't mentioned in the examinations, right? So it's no need to go directly just solve by the hand. So in every examinations, they will be providing with the scientific calculator, like digital scientific calculator on the top of the, while you will be giving the examinations, or if you're giving it an offline mode, you will have a scientific calculator. So put this equation directly in the scientific calculator. Okay, so the final answer comes out to be 4200 per mole. Okay. Now the second thing is what they have asked is the change in, so we calculated this one. Now second they have asked is change in the entropy of the gas taken from state. Okay, so this is the first one. We'll go to the second one. Then the change in entropy is given by equation Cp by T dt minus so this is also the sorry guys, equation that is come up directly was not by just I've not made up these equations. I've written these equations because it has been uh, to see whether it's covered or not, but it's like uh, the change in the systems, the change in entropy, the change in enthalpy, the change in the temperature and pressure, and how these are related to the thermodynamic network systems. So this all these things has been derived from the thermodynamic networks, and the particular arrived at a point, the change in enthalpy, how to relate the change in enthalpy with the thermodynamic network systems, how to relate the entropy change with the thermodynamic network systems. So if you see all these equations related, this can be related directly to the thermodynamic network, what I've shown probably, and the same can also be related to the Maxwell equations. Okay, so if you know all these relationships like thermodynamic relationships and the Maxwell relationships, it's easier to for you to solve these questions. So also so ds equal to cp ln t2 by t1 minus rn p2 by p1. Okay, so what I've done, I've taken the specific constant pressure cp out as constant, and I've integrated dt by t with respect to t1 to t2. Similarly, I've taken the universal gas constant r outside a constant, and I integrated these two things. Okay, from t1 to t2 and p1 to p2, so you can arrive at this question. So just put all the values. So specific heat at cp is given as 40 ln of t2 by t1. So t2 is 400 by 300 minus r is 8.31451 joule per mole Kelvin. Ln of p2 is 20 and p1 is 10. Solve this answer, it would be, this is in kilojoule Kelvin. So yes. Okay, so what I've been saying is that it's just the it's just the relationships that you need to take care of, how to arrive at a particular relationships. Okay, so if you know all the basic equations like internal energy h equal to u plus u, that is enthalpy, internal energy u equal to q plus uh, delta w, w is the work done during the process, that is integration p dv from volume 1 to volume 2, and from that enthalpy h equal to u plus v keeps free energy, that's h equal to u minus ts, and similarly Helmholtz gives free energy equal to the similar equations. So after that only we do the partial differentiations of the solve these equations and try to arrive at a relationship which is called as a Maxwell relationships, and how this all these relationships can be related to each other either by a cyclic relationships or a linear relationship with each other. So we have seen in today's content is that how what are thermodynamic networks and how these relationships can be related in order to solve some of the numericals. So if you don't know the thermodynamic network or the Maxwell relationships, you will not be able to solve these numericals for sure. So don't mug up the equations, just remember the basic equations of Gibbs free energy, Helmholtz free energy, internal energy, enthalpy. Try to partial differentiate. If you don't know partial differentiate, go Google it out, check out how to do partial differentiation. It's very much easier because it doesn't include complex partial differentiation or differentiation terms. So it's just like you have to differentiate at constant temperature and pressure and volume and entropy, and you will arrive at the different relationships. So once you know the different relationships, you can directly solve this, like, numericals in a quick short of span of time like 3 to 4 minutes. Okay. Now what we'll do is we'll solve another question. So, uh, like I said, we'll start from some of the small numericals, then we'll try to build up some space. So I don't want to just directly quick jump on the hardest numericals in the one go, because some of you might don't know what is going on here, what is going to happen further. So if we start from the scratch and try to build up on the base foundation, it will be good for all you guys. Okay, so this is another equation which covers the concepts of the week 1 and week 2. Okay, so we'll see. So the question says at 1 bar and between 283 Kelvin and 363 Kelvin. So the T1 and T2 is given and P1 is given to us as 1 bar. The volume expansivity, like I said, volume expansivity beta for water in Kelvin per Kelvin is given to us as this thing. And the isothermal compressibility will be given as kappa. Kappa this or this thing. Okay. Oh, sorry. So we already solved one of the equation related to the volume expansivity beta. Okay. So now here what is given to us is directly the equation for the volume expansivity. We are given temperature T1 and T2 and the pressure is P1. So what is given to us is the density of water at 300 Kelvin is and 1 bar is this. Its density at 350 Kelvin. Okay. So they have given density of water at suppose at 300 Kelvin 1 bar is 996 kg per meter cube. And they have asked density of water at 350 Kelvin and 1 bar. So what will the density? Okay, so if the temperature increases, what will happen to the expansivity of the water? So they have asked. So the simplest thing is that if you take a water system which is having a water at a normal temperature pressure, there will be some volume will occupied by the system. If you increase the temperature, water will start to boil and require much more volume compared to the prior system because it's now not in equilibrium. Okay, so it will form water vapor and water, there will be two different phases. So it will increase the volume of the system will increase. So the volume expansion will be there and that can be related to the volume expansivity beta. So here what they have given is that this is that the density is at 300 Kelvin, 1 bar is 996. Now they want to say if we increase the temperature to 350 Kelvin, what will be the volume expansivity keeping the pressure constant at 1 bar. Okay, so you write what has been given to us. First of all, so volume expansion beta is given as 28.104 minus 769.7 by 10 is to minus 4. Okay, and we have been given density, oh sorry, rho 1 is 19 kg per meter cube, temperature 1 is given to us as 300 Kelvin, P1 is 1 bar, T2 is given to us 50 Kelvin and P2 is constant, that is at 1 bar. So we have to find rho 2. Okay, so what we'll do that is volume expansivity beta divided by B is equal to beta. Yeah, so this can be written as beta equal to 1 upon del V by del T constant pressure, right? So this is what is volume expansivity beta. I've expanded in terms of this thing. So the pressure is already constant, P1 equal to P2, that is at given at 1 bar. So if I take pressure constant, we will give it dV by V equal to beta into dt. So what has been given up here? Okay, so now we know that density is equal to 1 upon volume. Okay, and this can be related to I'm trying to simplify some of the equations because I am going to relate with this equation as of now, these two. Okay, so I am simplifying the equation and this turns out to be therefore d2 by rho Okay. Now what we'll do is that we'll integrate between rho1 to rho2. So if we integrate these two things, we will get ln of rho2 by rho1 equal to minus integration t1 is 300, t2 is 350. They have asked beta equation is given to us as, we will type this entire equation up here, 28.104 minus 7639.7 by t 10 is to minus 4 dt. So just try to solve this equation. Keep T1 as 300 and T2 as 350 degrees Celsius. Rho1 we already know. Rho1 given to us as 996. Try to solve this. Take ln on the opposite side. There will be an exponential, that is e raised to that term. So if we try to solve it out, Rho2 will come out to be 973.59 kg per meter. Okay, so what you have to do is just like differentiate, partial differentiate. So instead of T, it will be T2 minus T1. There will be two different temperatures and both has been given to us. So T1 is 300, T2 is 350. That I've taken the limits up here. Rho1 is given to us as 996 kg per meter cube. So what I have to do, just solve on the RHS side first of all. Try to just come to a particular value. Then what you do is that take ln on the right hand side. So it will be exponential of that term. And just multiply it with the rho1 value that is given to us. So it will come at a final answer, that is rho2 is 973.59. Okay, so this is how you can relate like the thermodynamic relationship network or the Maxwell relationships in order to solve a question. Just solve two more quick questions for today, and then we'll wind up the today's biointeractive sessions. So this reason why I'm solving this question is that just for like brushing up the concepts for the entire weekend. So if you know some of the concepts during the weekend that has been covered in the forms of the numericals that we solved, you will remember that much in a deeper sense, apart from just saying the concepts that has been discussed. So unless and until you use this concept to solve the numericals, it's not going to play any role. But if you have been given some questions, you know the concepts and you try to solve them on it your own, you get a much more deep interest in the subject, right? So that's what we are doing it right now here. Okay. So if you go to the question that has been given is that 320 gram of methane, which has a molar mass of 16 gram per mole at temperature of 600 Kelvin and pressure of 10 bar, undergoes an isobaric. There is a constant pressure process to a temperature of T2 is 300 Kelvin. Assume methane to be an ideal gas in these conditions with specific heat at constant pressure is given as, for an ideal gas it is 29 joule per mole Kelvin. The pressure is irreversible and it exchanges the heat of this, that is the heat exchanges minus that is giving the heat. The efficiency in percentage of this reversible process rounded up to the nearest integer. Okay, so we'll try to quickly start bringing what has been given in the question. Okay. So if you can see, the system is in the condition which is closed. So we'll say that the system is closed. And grams of methane, the molar mass is given. So the number of moles will take. What is the number of moles of methane? N equal to given weight by molecular weight. So the given weight is 320 and the molar mass is 16. So it's 20 moles of methane. So now we have to calculate the efficiency. Okay. Now this is irreversible. The process is reversible. Okay. So now we know that the work done in a reversible process is equal to integration n Cp dt and Cp delta t. Therefore Q reversible equal to, now since press specific heat constant, we can take this out. We have taken this out and the differential reaction. So number of moles is 20. Cp is given to us 29. Temperature is T2 minus T1, that is 300 minus 600. This comes out to be negative as minus 174 kilojoule. Now the work done during the reversible process. So this is the heat heat during the reversal process. Now we'll calculate the work done. So now work W is equal to PdV, right? So work done during the process is integration PdV. So work done during the reversal process will be number of moles into minus. So I will try to differentiate partially. I will try to read the ideal gas law because it's given ideal gas. This comes out to a minus 20 to 8.1451 to 300 minus 600. It comes out to be 49.88 kilojoule. Okay, so this is the work done during the reversal process. Now, the main thing that has been given to us is the work is greater than 0. So the work is, so you can see the work done during the reversal process is positive. So work is done on the system. So W is greater than 0. We have given work done is greater than 0. This means work is done on the system. Now we relate the internal energy Q is equal to U plus U equal to Q plus U. That is from the first law. Now we have Q reversible and W reversible. If you take both the terms here, it will comes out to be 1 minus 24. So how this comes is that we already have calculated the work done during the reversal process and the work done, heat during the reversal process and the work done during the reversal process. Just plus these two things, because Q reversible is negative and W reversible is positive. The final answer is this thing. Now what we'll do is that we need to find out what is the final thing, the efficiency of this irreversible process. So we need to find out for the irreversible process. Till now we are working on the reversible. So now the another main thing, since this is the internal energy is a state function, so it will be the same for both the reversible and the irreversible. Therefore del ut equal to Q irreversible W irreversible comes out to be minus 124.116 minus Q irreversible is plus 186.4. So the work done during the reversible process is positive. Now efficiency will be work during the reversible process minus work done during the reversible process. So work done during the reversible process is 49.88. Work done during the reversible process is 62.28. Comes out to be 0.81 approximately 0.801. So approximately 80% is the answer. Okay. So this is how the simple things is, just like you need to know what are the different terms, what is reversible. So this is the first week content that I have discussed. What are different types of processes, what is reversible process, what is irreversible process. So if you know how to write U equal to H plus VV, U equal to Q plus LW, with the reversible and irreversible, it will be much more helpful. And if you know what are state function and path functions, like I mentioned, internal energy delta U is a state function, so the work done during the reversible and irreversible process will be the same. So since I calculated for the reversible, it can be related directly for the irreversible also. Okay, and I have just calculated the efficiency, that is work done during the reversible process divided by work done during the irreversible process. Okay, So the last question for today. So what I've been given in the question is that 5 moles of an ideal gas undergoes mechanical reversible adiabatic compression from 1 bar to 10 bar. So number of moles of an ideal gas is 5 and equal to 5 moles. Reversible adiabatic process, that is Q equal to 0 from P1 equal to 1 bar to P2 equal to 10 bar. The specific heat at constant pressure is going to assess 30 joule per mole Kelvin. If the initial temperature, that is T1, is 300 Kelvin, total volume of the gas in liters rounded off to the, okay, so we need to find the volume of the gas. So what we'll do, we'll know the distance in ideal gas PV equal to nRT. Now V1 equal to RT1 by P1. Okay. So R equal to 8.31451 joule per mole Kelvin into T1 is given to us as 300 Kelvin divided by P1 pressure as 1 bar. So it convert into Pascal. That is 1 is equal to 10 to 5 Pascal. This comes out to be 0.024 meter cube per mole. Now for a reversible adiabatic compression. So what we'll do is that for reversible adiabatic process, we have PV raised to gamma is equal to P1 V1 raised to gamma equal to P2 V2 raised to gamma. Therefore, V2 raised to gamma equal to P1 raised to gamma P2. Now I have P1. P1 is given to us. P1 is given to us. P2 is given to us. Okay. So specific constant pressure is 30. Okay. So if you solve this thing, you will be able to derive V2 from here. That is V2 is 1 raised to gamma. So what will come? Gamma will come on the right hand side. It will come up here. Okay. Take the gamma constant. Now, the another important relationships that I've not just discussed as of now is that the relationship between the specific heat at constant pressure and specific heat at constant volume. So it is minus Cp minus Cv equal to R. Therefore, gamma and also gamma equal to Cp by Cv. Therefore, Cp and Cv can be found from this equation is Cp minus R. Now, specific heat at constant pressure is given as 30. And R is universal gas constant. Okay. So gamma comes out to be 1 point. Now we know V2 is 6.0 from the previous equation that I've derived. 1 by gamma turns out to be 1.38. Therefore V2, if you try to solve it out, it comes out to be 0.0047 meter cube per mole. So the total volume, now the final question is that we need to determine the total volume in liters. Okay, so total volume is V2 total is equal to N into V2. Number of moles is 5 into 0.0047. This turns out to be, it will be in meter cube, that is 0.023 and 1 meter cube is 1000 liters. So let's convert into this. So it will be 23.6 liters. Okay. So this is some of the relationships that I'm not discussed in the content today, but I wanted to solve directly the numericals instead of discussing directly the contents what has been covered. So these are some of the things that it's better for like everyone to go through the concepts first of all, because I know these are trickiest point to solve some of the points in the examinations, but if you don't know the concepts, it will be very hard because at some point of time I also got forgot what are how to relate some of the terms with each other, how to arrive at a final answer, how to relate the different relationships, thermodynamic relationships with each other. So it just comes from the practice. So what I would suggest that do practice like 1 hour, 2 hour, like not every day, but like an alternative days. Half an hour will also be sufficient for doing the big content. If you cover the big content within half an hour or 1 hour on the alternative days, so it will be helpful for you guys because at a later points it will be much more. It's going to get more complex because these are just an ideal equations of state. That is an ideal gas equation of state PV equal to nRT. So in real world, there will be no ideal equation, ideal states. There will be no ideal system. There will be non-ideal systems, and for that, we'll be having different non-ideal equations of state, like I told Van der Waals equation of state, so Redlich-Kong, and Penn-Robinson. And these equation states are much more complex, and for solving that, it will take, if it's in examinations like in undergrad BTech examinations, it will take if your examiner is giving a full length question, it will take 1 hour to solve the entire question also for like this equation of states. So please do not rush up. Just try to go through the concepts what we are building up right now. It will be helpful for you only. Okay. So this is what I have for today. So what we covered is that covered the thermodynamic relationships, Maxwell relationships. We solved some of the MCQs like the quick shorts MCQ and some of the concepts related to the numericals related to the concepts that has been covered during the week 1 and week 2 both, and some of the concepts related to the non-ideal equation of state. The equation, the one equation that we solved is based on the Van der Waals equation of state, but we are not discussing the course like in the live interactive session now. So what we'll do is that from next week we'll discuss some of the non-ideal equation of states also, and plus the lecture content of the week 3 for better and smooth process towards the end. So apart from this, if you have any issues related to any numericals, any assignment problems, only if the assignment problems due date has been ended and the solution has been uploaded on the NPTEL assignment portal, you can ask the solutions towards me. If you don't understand the solution that has been uploaded, please do ask me out. Uh, Apart from this, this is what I have for today. We'll meet next week on the same time, that is on Saturday, 3 to 5 p.m. So it's not like just confined to 3 to 5. If you can complete up it in like 1.5 hours, or even if it goes about 2 hours, I'll be happy to continue with that about 2 hours or 3 hours also. But since I don't want to just like rush through all the contents within one go, it's like I'm building some of the foundations for you guys only, just for helping you out for the final examinations and for the better understanding of the course. Okay. In meantime, if you have any issues related to the course content on the way I am teaching, please do let me know on the NPTEL portal. There is a forum. You can also put up your questions upset or contact through the mail ID, through your official mail ID. And plus, you can ask questions anywhere in between. If you want to ask anywhere in the between when I'm solving, do ping me out. I will be happy to help you out in between the question itself. It's not like you have to stay till the end and then you will ask some questions on the questions. Do pinch me, do bug me in between when I'm solving any of the questions or discussing any of the concepts, because at some point I'll think that what I've discussed I might have forgot at the end point. But if it's in between of the discussion, it will be helpful for you and for the others also, because it will be a live interactive session for you as well as me, and for the other students will also be get benefited from the same. Okay, so this is what I have for today. See you next time. Till then, yeah, thank you. Yeah, please go ahead. Rajiv. Rajiv, I'm not able to hear you. Just 1 minute. Can you speak up right now? Rajiv, your voice is not audible actually. Can you just type a message in the chat box? Rajiv, your voice is not audible. Can you type a message in the chat box, please? Okay, Rajesh. So this notes has been already been uploaded on the NPTEL Swim portal. Don't worry about anything. Nothing can be shared on the mail ID. You can go to the NPTEL Swim portal from where you are accessing the assignments as well as the lecture notes. At the extreme bottom, there will be lectures. The same lecture I am recording, it will be uploaded directly there. Plus, there will be a lecture notes also. So, what I will doing is that I will be uploading the same thing in the form of a PDF directly onto the portal. So, you can access to the NPTEL Swayam portal itself. Okay. Rajiv, your voice is not audible. If anything is there, you can just type a message in the chat box, please. Okay, so all the week lecture notes, that is a live interactive sessions, what I am discussing in the PPT, will be uploaded in the form of a PDF in the NPTEL Swim portal. Apart from that, all these live interactive sessions have been recorded. So all this will be uploaded on the YouTube also. So you can see to the YouTube that the link has already been given to you guys on the NPTEL Swim portal itself. At the extreme bottom, there will be an option of download videos. You can download the week-wise videos also. You can watch on the YouTube also. Plus, all the lecture notes, what I'm solving up here in the form of PDF, will also be uploaded in the NPTEL Student portal. So you don't have to worry about anything. All things will be there on the portal itself. Videos plus the lecture notes plus what I'm discussing right now here in the form of a PDF. Okay. Is there anything else? Okay, if there is nothing, we will meet next week on the same time, like Saturday 3 to 5. Till then, see you. Take care. Goodbye.